Wow, that doesn't look too good. Okay, I guess we're gonna have some translation issues, but let me just say before Carly's amazing Persephone study, there was a SWIRI internal study that I led with internal research money to look at what we call the gold standard. And I'm going to tell you about that. And it led directly to what Carly's just told you about. And oops, I wanted to just point out, and I don't know how to go backwards, but there was a whole team of people on that. The red button goes backwards. I don't like pushing red buttons. You never know. Okay, I just want to point out Mark Tapley and a whole bunch of people at Southwest worked on this. And then, the basis of it is, there's no substitute for proximity. And that's the far side of Pluto that you see on the left. And we really don't know what's going on there. And there's so many questions following New Horizons that require deeper investigation. And obviously the thing to do is an orbiter. So you have time domain, but you also have the time not just to take, but to downlink vast quantities of data, much higher resolution mapping data sets, spectral mapping data sets, studying the atmosphere in new ways, actually doing in situ measurements of the atmosphere, like with a mass spectrometer. And of course, a really competent satellite tour. Except for Sharon, we only did very cursory satellite science on New Horizons. So the debate that normally takes place for those of us that are interested in this kind of science is, what should we do next? Should we do a Pluto mission and really go back and understand that world in depth? That requires an orbiter. Or should we go sample the diversity of things in the Kuiper Belt? And what we showed with the gold standard study and what led to Persephone is that you can do both. And that's why we called it the gold standard, is because you could break that competition as long as you were willing to put up with a very long mission. So you can combine both objectives. And we published this in a paper in 2020. The study took place in 2018 and 2019 in the early parts of 2020. And that's a Journal of Spacecraft and Rockets peer-reviewed paper, AIAA publication. And you can read that. But let me start with the bottom line up front, or BLUF. A spacecraft equipped for orbital reconnaissance of the Pluto system is also super well equipped to do the exploration of KBOs. And we sort of knew that, but we went to a lot more depth. Of course, New Horizons had a Pluto payload that went on to Arrokoth and is primed to do another flyby if we can find a target. So we sort of already knew that. And there were a lot of post-Pluto dwarf planet targets that we found we could reach with an electric propulsion system driven by RTGs. It's a little bit different, though, than what Carly talked about. And I'll point that out. And all of this fits within the mass you can lift with existing launch vehicles and reasonable spacecraft power and reasonable costs. And I'll talk about that. And en route from Pluto to one or more other dwarf planets, we also found that we could reach a lot of small KBOs along the way. So you could have it all, and you could do it for a reasonably affordable price. It wasn't nearly as extensive a payload as Carly's Persephone mission, but still a much more competent payload than New Horizons flew. And because these electric propulsion systems driven by RTGs instead of solar arrays are new. They've never been done, but really the electric propulsion system doesn't know where it's getting the wattage from, the current, right? There's a power system somewhere on the spacecraft, and propulsion just gets fed conditioned power. And so instead of driving it with solar arrays, we drive it with RTGs. But the hang up for all these missions is with our current technology, all of the solar electric propulsion systems, although they're very efficient, they have high specific impulse, they have low thrust. And that's what makes these missions very long. So if you remember, New Horizons launched as the fastest spacecraft ever launched to do a fast flyby of Pluto. Took 9.5 years to do the crossing, much faster than Voyager would have done it. But if you want to do an orbiter, you have to actually come to a stop. So classically, you thrust half, you go on a ballistic trajectory, and the second half of the trajectory is all braking. So it about doubles the flight time. Now, this is sort of an eye chart, but I just want to tell you that we did a full breakdown of the spacecraft mass requirements by subsystem, including reserves, and we looked at the power, and we show that both mass and power close. That is, that there are existing launch vehicles that can launch this system, and that we could do it on 3 RTGs. Now, 3 RTGs doesn't allow you to do all the things that you could do in Persephone, but it's a lot easier to get 3 than 5, although today it's hard to even get 1. And then we looked at the costs, and in 2020 dollars, it was 2.6 or 2.7 billion dollars to do this. This includes the launch vehicle. So, that's roughly the top end of new frontiers these days, a mission like Dragonfly. But it is a long mission. Again, we had a fly out time that's measured in over 2 decades, a 2-year orbital tour that was a very extensive orbital tour in which we really pioneered what Persephone was able to implement, which is using Charon to crank and reshape the orbit dozens of times to tour all throughout the Pluto system, all the satellites, to get the mass spectrometer down into the atmosphere for many, many, many passes, to study Charon, of course, to get all aspects of Pluto. We didn't have a low light level camera that came along with Persephone, but we made numerous close approaches to every one of the 5 satellites, and obviously did a spectacular job compared to what any flyby mission could do. And because Charon's doing all the heavy lifting, the gravity assists, we only needed propulsion on board for fine targeting, basically for very small maneuvers. And we were able to show, because we need a chemical propulsion system for that, you have to make impulsive maneuvers, that you could do it with a reasonable sized chemical propulsion system to carry out that whole tour. And of course, there are numerous close approaches to Pluto, and they get very much closer than New Horizons did, almost an order of magnitude closer. But we also found that we could get out of the system using a series of Charon flybys to more or less escape for free, and then get back into the Kuiper Belt, where the electric propulsion is then used to take you on a tour of small KBOs en route. That's just a cartoon of the Pluto escape. But then going on, after Pluto departure, in this case, the study was a Pluto system departure in mid-June of 2041. And then we would use the electric propulsion to go on to dwarf planets with small KBOs en route. And we showed that there were lots of dwarf planet candidates that we could get to in reasonable flight times, something like 7-8 years for the first one. And that on the way to any of these, we could get a number of small KBOs so that we could make a comparative planetology context for what we found with Arrokoth on New Horizons. So overall, I think this was a really important and landmark study. It was a lot of work. It showed that we could break the common dichotomy between should we have an orbiter of Pluto or should we have the next Kuiper Belt mission, that you can do both. You just have to, with today's technology, live with 40 and 50-year-long missions, which they're not impossible. Hubble Space Telescope's been in orbit well over almost 35 years now. And of course, Voyager's 47 or 48 years since it's been launched. We know how to do these things, but you have to be patient and you have to plan for it very carefully, because you're going to transfer knowledge multiple times between different teams of people who built it, then maybe fly it to Pluto, then maybe fly it out in the Kuiper Belt. It might be a 3-generation type mission. So you have to be careful to make sure that you don't make mistakes when you do that. We did that on New Horizons too. We called it longevity planning. Because the mission we started in 2001 when we were selected. Here it is, essentially 25 years later, we're still flying it. And New Horizons has the capability to fly another 25 years as far as power and fuel and comm range are concerned. So from a technical basis, and that's what Gold Standard is all about. I'd be happy to answer questions.
We have lots of time for questions. I encourage you to use it.
So one difference between a 20 or 30-year long mission like Hubble with what you're proposing with Gold Standard, and to some extent you face this problem with New Horizons, is engagement, public engagement, political engagement. How do you solve that problem And is that a hurdle to getting a mission like this approved?
Well, I think the hardest part of the engagement is the 20 years, or in the case of Persephone, almost 30 years to get to the primary target, to get to Pluto. It's a lot of delayed gratification along the way, right? And I found it very hard when we were trying to sell Pluto missions in the 90s. A lot of people didn't want to have any part of it because it would take so long that they couldn't benefit in their career span. In particular, the people who were in the position of making decisions were typically in the second half of their career. And for them, there was going to be no benefit. They weren't going to be able to do anything with the data by the time that we could get it. It's even harder in a case like this. I think that the big difference, now that we know that the decadal didn't select a mission like this, and we can look to the future, there are some very interesting developments that are taking place in the electric propulsion community to do much higher thrust electric propulsion. And some of it's going to be very expensive, which would drive the mission cost up, but could cut the flight times down by a factor of 2 or 3. So I think by the time this is seriously re-entertained in 1 or 2 decadal surveys, we'll probably have propulsion that'll make this, instead of a 50-year mission, more like a 15-year mission, something of that order, and I don't think that'll be so hard.
Hey, I wondered if you wanted to talk about the payload that you had a little bit, because you didn't really mention that too
I
much.
didn't mention the payload, but it was basically a New Horizons payload plus a mass spectrometer and a thermal instrument and a more complete plasma package that included a magnetometer, for example, but didn't include the low light level cameras and some of the other things that Persephone could afford to do on a much bigger budget.
Thanks.
I have a quick question. Actually, it's for Ralph, I think. What is the present production rate of plutonium or RTGs? And how, if we just keep going the way we are, how many per year? Yeah.
How many RTGs per decade?
Yeah, that's what I'm asking. Exactly.
So it depends on the RTG. So right now, what the philosophy that has been adopted by NASA and DOE, or had been 10 years ago, it's what's called constant rate production. And the aim point is to make 1.5 kilograms per year of plutonium-238. And just do that on a continuing basis. You put it on the shelf. Some of it's going to decay. So it depends on when you fly. And part of the problem in all this has been that NASA does not have a uniform cadence of when that you fly things. 1.5 kilograms per year is basically what we have used over the last 50 years that has fit the amount of budget that NASA has put into to unmanned spacecraft. And that's where that 1.5 kilograms per year came from. To support that, right now, NASA has been sending over to the Department of Energy approximately $120 million per year, because NASA is paying for the assembly line, they're paying for the people, they're paying for the facilities, they're paying for all the materials, because the other customers within the government that existed 50 years ago no longer exist. And that's not something that we can go into any detail about, not in this forum and not in most forums. But that's where the setup is. And right now, what's going on in the Senate is of critical note to all of this, because in the president's budget request, right now, the plan is to shut down the entire assembly line by FY29, no more plutonium-238 production, because, quote unquote, we don't have any more missions that are going to be needing it. And if the line gets shut down for as much as 1 or 2 years with everything that is going on, you're never going to be able to reestablish it for less than, probably, I'm guessing, at least $1 billion, and will probably take you 6 or 7 years, because the facilities are oversubscribed. And if this stuff goes away, everybody else is going to get their claws into it about building microreactors and looking at new kinds of reactor fuel. So what is happening right now in Washington is incredibly important for being able to maintain this sort of capability for going forward into the future. And no, americium-241 doesn't work. You've got the same kind of cost problems, and you've got even more technical risk. A lot of details there, and we can have a drink about that because it'd take me too long to explain it. But that's kind of where we are. So there are a lot of really critical things going on if we are going to keep exploring any part of the solar system past the orbit of Jupiter.
Well, thank you for sharing that very important information.
Our
And let's
next-
thank Alan again.